Thank you. All right, so like they mentioned, today I'm going to be talking about optimizing for LCP and Angular applications. My agenda today is that I'm first going to be talking about what exactly is LCP and why you should care about it. After that, I'm going to be talking about a model that you can use to think about how to optimize it, which is framework agnostic. And then I'm going to go through a couple of techniques that are Angular specific and framework agnostic, and recap the whole thing. The application that I'm going to be using as a demo is the one that you see here. It's an app that I built that functions as a listing page for a whole bunch of different boats. You can see the before as how it started, where the application takes around 3.5 seconds to load. And inside of the application, after we've finished all the improvements, the application takes only 2.5 seconds to load. Essentially, I'm going to be walking you through how to take any application and do something similar to that. Just going to wait until it finishes loading. Wait for, and okay. So, what is LCP, right? So there's something important that I like to talk about when it comes to LCP, and that is that there is actually a large difference in between what it's intended to be and what it actually means. So there is a fundamental difference in between what it's actually intended to be, the meaning behind it, and what it actually is in a literal terms. Because you see, what it actually is an API that will measure every time there is a larger element being rendered on a page, or on the browser or in the viewport. It'll measure that from the beginning of a navigation to the end of a navigation, or until a user interacts with the page. But what it's actually intended to mean, or what it's intended to be, is a metric that'll tell you when is the page loaded, when is the page useful, and when does it feel like it's completed. So it's user-centric. It's for perceived load performance, not actual load performance. It's supposed to be the main piece of content, not just any piece of content or the largest piece of content on the page. And it's supposed to reassure the user that whatever is on the page is useful. Here is an interesting example, and I'll show you another one of why it's important to make that distinction. And it's about showing the most important and useful piece of information first. So when the page starts loading, the first thing that will reassure a user that the page is useful is having the search on the top, where you can see that it's indeed the search that you're going for. After that, we have the actual title, and it reassures you. But the next piece of data that it'll show in the top image is the description of the page. Google originally had it like this maybe 4 years ago, and they optimized the page to load differently. So instead of loading the content first, they decided to load the main image. So as you can see in the second images in the bottom, is that we're now going to be loading the description, like the search at first, and then the title of the search, but then the image. Because even though it's not the largest piece of content, it definitely will reassure a user that it's useful again. And then the actual description. An interesting example of where largest contentful paint might fail to measure what it's intended to is inside of this application. So if you look at the first thing that it marks as the largest contentful paint, it's a hero text. It's just a little description of what the page does. Definitely something useful at the beginning. Then it's a loading image. And then it's the actual image that is probably what the user came to see. That is for a mobile device though. For a desktop, it'll just register the banner, the hero text. And I don't think that that is the most useful piece of content. So when I'm talking about optimizing LCP, I don't mean the hero text. I mean the most important, the main piece of content is actually valuable for your application and for your users. And now that you understand why, or what exactly is LCP, let's get into why you should care. And the reason is actually really straightforward. Your users actually really care. We can go and look at a couple case studies. This is from 2015 and 2016. Pinterest decreased their load time by 40%. That increased SEO traffic by 15% and increased signed up by 50%. This is also what they attribute the largest part of their growth in 2016, or at least the beginning of 2016. Cook is an e-commerce platform. Essentially, you can buy cooking goods and frozen foods, from what I understand. They decreased their load time by 850 milliseconds, and increased conversion by 7%, and increased pages per session by 10%. So those are actually pretty massive metrics. But the reason why I'm talking about it now, why it's important to think about it for you, is because it turns out that the majority of applications struggle with this. This is the metric, the core web vital, that people struggle with the most. We can see that largest contentful paint, only 52% of the applications achieve a good score. A good score means under 2.5 seconds to load the largest piece of content, even though it's intended to be the main piece of content. When LCP, 70% of applications passed, and first input delay, 95% of applications passed. So there's definitely a need to look at your applications and look if you need to optimize for LCP. And the next part about this is thinking about, like, what's the main part of it? And the main part of improving LCP is to understand when you should load things. What's the right moment in time to load something? The way I see it, you should do things as late as possible, but before it's actually needed. So essentially, you don't want to do work beforehand that's going to cause you not to, or to take more time doing other work, but you want to do it before the user is actually going to consume it. And to help explain how to improve this, I'm going to use the same model that Enea used earlier today. This is a model created by Google that will help us understand how to improve LCP by showing us a timeline of what loads on a page and what renders on a page that will conduct to this situation. So on this, you'll see the time to first byte, which is what Enea talked about, the resource load delay, where we're going to load any type of files that are necessary for us to then be able to load the largest contentful paint, and then the resource render delay, which is going to be all the time that it takes from the moment that the browser actually has the largest contentful paint to the moment it's actually ready to render it. This is a nice little breakdown of how an application should look, what applications perform the best, and how much time from the beginning of the navigation to the largest contentful paint should be consumed by every section. So, now, let's get into it. As I mentioned, I'm going to go through this application, and I'm going to walk you through all these little improvements that we can do that will eventually transform the load time from 3.5 seconds to 2.5 in this application, but that you can use and implement in your own applications. I'm going to do that by moving the request to the parent component or the container component, and after that, I'm going to move it further back into a route resolver. After that, even further back into an app initializer. And after that, I'm going to do something a little bit different, where I'm going to use preload tags to load the data itself inside of the HTML and the LCP inside of the app initializer. Finally, I'll talk about resource load time, how to improve it with some image optimizations, size, formatting, and a couple of other things were already mentioned today. So, as you can see, I'm only going to be talking about resource load delay and resource load time. Today we've already had a couple of conversations about how to improve the other sections. For example, we had Enea's talk that explained how to reduce time to first byte. So if you're looking to learn more about that, you can probably find his video that will explain in more detail afterwards. Now, let's take a look at the initial state of our applications. This is the application, right? And essentially what we want to do is improve the load speed of that first image so that we actually get it to load. This is accurate representation of how much time the browser spends doing all the things and when things actually load on a 3G mobile device, right? As you can see, the browser rendering that happens at the end is very minimal. So it doesn't affect the application. That's why I'm not focusing on that part, for this use case at least. You'll see there that also all the things that are happening in the middle are the framework-related things, and then we download the data and from there forward. Another little breakdown of how the application loads, the amount of time that it spends during each one of these 4 sections. It goes from 20% for the time to first byte. Resource load delay is 60% basically, which is huge. 20% for resource load time, and only 1% for the render delay. So let's start with the optimizations on resource load delay. Again, the little breakdown. And now it's the actual application, the real example of it. You can see, like I mentioned, we load the document. After we've loaded the document, we load all the framework-related things, and then we fetch the data, and after we're done with the data, we get the LCP and render the LCP. Not much time in between the moment that we've loaded the data and rendered it on the page. So, the first optimization I would like to talk to you about. It's about moving the HTTP request, or initializing that request, inside of the container component at the top of the render tree. So, here is a little bit more of a detailed breakdown of it. Inside of the framework, of the things that we load from the framework and we do that are directly related to Angular, we have the display part. But we also have a container, which is part of the componentry, and I'll explain that in a little bit more detail in a second. Essentially, right now, in the basic application, it actually initializes the request from the display component, which looks like this. For example, this is an example using RxLet that'll actually initialize the request inside of the display component, as you can see. So what is this container component and display component that I'm talking about? I'll go a little bit more in detail in a second, but essentially the container component is whatever is wrapping it, for example, a feature component or a route component, and the display component are every one of the components that are inside of there that are actually going to be showing the data and doing things directly with the data. Another good representation for it, the one marked as A is the container component, and every single one of the ones below it are all display components, and then we have a general state of the application. And in the example that I showed you, in the code that I showed you before, we'd be fetching the data or initializing and triggering the fetch request from within the display component, which is all the way in the bottom. Well, you can see that there is a lot of things that happen between the moment that the container actually loads to the moment that the display component actually renders and then triggers the fetch request. So, why not just load it inside of the container component? Essentially, that just means that we trigger that initial request further up inside of the container component. It's an example of code for that. And by doing that, we'd eliminate that time that it takes to render. Another example of it. And then again, since it is a global state, the image, it'll still be used inside of the display component. So by doing that, we will move the trigger back from the end of the display component to the beginning of the component. And inside of the real application, you can see on the right side that the thing that is marked as a display component there is where it would have been triggered, and the one that's marked on the left side as the container is where it was actually triggered by calling it or triggering it inside of the container component. The next thing is to move it even further back inside of a route resolver. Instead of fetching the data or initializing the fetch inside of the component, we can actually fetch it as part of the route or the navigation event. All right? So, essentially it's this. We're going to move the request even further back into the route resolver, which is an event that'll happen inside of the navigation event. All right? Here is an example in which I'm getting the data, and of course there are many ways to do this. You can either wait until the data finishes downloading, which would pause the bootstrapping of the application, or you can do this asynchronously and just consume the data but initiate the request inside of the route resolver. So what this means is that we would actually be able to move it all the way back. And so as you can see there, I am now loading the piece of data at the same time as I'm loading my lazy loaded feature module, my container module, which means that it has now moved considerably further back. Well, the next part is to move it even further back and to initialize the fetching of the data inside of the app initializer. Essentially, the app initializer is the first moment in time inside of an Angular application where you can actually do things. And so, as you can see there, we'd be doing it before the container has rendered, before the route has been initiated, and inside of the framework itself. So, here is a nice little example, and like I mentioned, this is the first moment in time where you can actually run code and initialize things inside of an Angular application. And as you can see here, I have now initiated the fetch request, which is now available, the data is now available much earlier by fetching it directly inside of the app initializer. But you can see that that didn't really make a change there. It didn't actually improve the LCP because we already had the data at the end of the loading of the route, of the feature module. So even though we've moved it further back, we didn't actually save time because no new work was ready to be done. And so we loaded it too soon and we just wasted a little time. But by doing that, we now have the data available much, much sooner inside of the application. But we can push it even further back. And what we can do is, instead of loading it inside of the application, we can load it directly inside of the HTML. That means that as the document is loading, we're going to be loading the data. And as we do that, we can actually intercept the data inside of the app initializer and use the data for whatever purposes we actually need. This can be done using a link tag. And essentially, you have to do a fetch request with it. And after that, whenever you initiate a fetch request that is exactly the same as that one, it will not duplicate the fetch request, but fetch data from the browser itself. So, as you can see, now it has moved further back in time and is no longer as part of the app initializer, but actually inside of the HTML itself is where it's actually pulling in that data. Also, still no improvement to LCP. I have the data even earlier, but hey, didn't really make a difference because I still have to wait until the page loads to get the image. So, the next thing that we need to do is work on what's it called, reducing the amount of time or when the image is actually loaded. So, exactly in the same way that we loaded the data inside of the app initializer and inside of the document itself, we can now inject a link tag in the app initializer instead of the head of the document that will actually initialize the image when the data has finished loading. So you can see here where the data would usually, the image would actually be loading, but since the data is available much earlier and the app initializer has already access to the data, we can actually initiate the fetch request, the image downloading there, and consume it when we need it. So, essentially this is what it would look like. You download the data, and once the data is available and the app initializer is there, we can initiate the loading of the image. Once that's complete, we keep on doing our usual thing. The next part, now that that has been done, is to actually optimize the resource that we're actually loading. We already had a little bit of an explanation about how to optimize images in general. So I won't go too far into detail there, but there are a couple of essential things that I would like to mention. The first thing is that when we optimize images, most of the time, images are actually way too large. For some reason, we always load images that have an intrinsic value that is 4 to 10 times the size of whatever we are using. And that isn't most applications. So if you look at your applications, it's very likely that you're doing that yourself. So if we actually transform the image to be using the size that it is actually using, just cutting it and actually resizing the image, it'll be 4 times smaller in this case. And this is also kind of from a real application. So this is not a made-up example. It's actually something that's currently in production somewhere. So what happens if you have images that are different sizes that need to be displayed on different devices? What happens if you need to display a large image on a desktop and a smaller image on a mobile device? You can use something like a picture element that will then allow you to specify multiple sources. So if it is a mobile device, it will load the image 2 or the mini image, and if it is larger than that, or if that condition does not pass, it will load the next one. The next thing that we can do is use a next generation format. Most websites actually end up using JPEG or PNG, but there are other formats that are actually much more performant for downloading things on browsers. For example, we have WebP, and so here you'll see that on average a JPEG image will be 25 to 35% smaller when converted to WebP. This is for lossy compression, but yes. And WebP is now practically available everywhere, so there is really no reason not to use it, except for Internet Explorer, but we've no longer used Internet Explorer as much, so that's one example of that. However, there is also a newer format that we can use that is even more performant. That one, however, does have an issue with different browsers. It's not available on all browsers. So what we can do is, in the same way that we were passing different sources for different size of images, we can do exactly the same thing with the formats. If it can accept AVIF, it will take AVIF, but if that one doesn't go, it'll take WebP, and if that one doesn't go, it'll just take whatever is next as a source. However, you can actually combine all these. Essentially, you can choose the image that is the right size, and it'll just choose the first available one that matches the conditions of the current browser. So if it is the size and it accepts AVIF, it will take the first one. So this is the real world application again, and just making that transformation, we changed it from that to that, which is a very large optimization. It's more than 4 times smaller, right? The next thing to talk about is NG optimized image. And we've already had a conversation about it today, so I won't go into too much detail, as it was a wonderful explanation. But essentially, it's going to add a fetch priority. It will lazy load the images that are not inside of the viewport. It will let you know whether or not you're using pre-connect or whether or not you can do pre-loading on the server. It will enforce you to have a height and width so that you don't damage largest contentful paint, and it will allow you to use different sizes of images. I personally prefer to implement these best practices myself, but if it is a larger application and I have to apply it for a lot of things, this is a very safe way to go and ensures that, we won't have a regression. So I think that this is about 8 kilobytes that it'll increase, but your implementation will also have some sort of a cost. Okay, so let me just recap over what we looked over today. Essentially, we move the request back, starting from a display component to the container component. After that, we moved it even further back in the timeline to the route resolver. Then we moved it even further back to an app initializer. Then, instead of fetching the request, the data directly inside of JavaScript, we injected a preload link tag to fetch the data inside of the index.html. And when the data was ready inside of the app initializer, we actually preloaded the images themselves. Then we talked a little bit about optimizing the images, changing the size and the format, and using some of the best practices. So let's review what we learned with the actual data. These are the actual timeline representations of how much time everything took inside of this application. As you can see, 20%, 60%, 20%, like I showed you before. This is the interesting one though. Now we've actually moved back the data, and once the data has finished downloading, which will depend on the internet speed and a couple things, it will load the image and then go ahead and render the image on the page. Now we've changed numbers considerably. Instead of it taking 60% of the time to inside of resource load delay, it only takes 41% of the time. The index.html and the time to first byte all of a sudden is considerably more, and the resource load delay, the load time has also increased percentage-wise because it takes so much less time. But it makes a lot more sense if you compare them next to each other. Same data. As you can see, even though the time to first byte has increased in percentage-wise, it didn't actually change time-wise. It's just everything took so much less time that the numbers were reevaluated. And essentially, that is how you will transform an application from taking around 3.5 seconds to load to 2.5 seconds to load. Yeah, so that's my talk, and thank you very much.